let me, I realized I'd gone over my notes and thought about what I said and realized this addition of angular momentum stuff, it starts out impossibly dense and like, oh, what in the heck is going on? I want to use different words there, but I'm on film. And it's actually one of the easiest things. It's actually kind of fun because it's actually like the way you're going to do this is using what's called the Clebsch-Gordon table, and it's actually like Dirac notation in that it takes some ridiculous mathematics and turns it into a picture. It's actually one of the easiest things you could do, but it starts out unbelievably complicated. And then what we're going to do is examples. So my description will probably blow your head off, and when we go through examples, you're like, how can those be the same thing? This is actually so easy. So just heads up on that. So don't get too frustrated. I've got a couple more lecture stuff to do, which will probably make things worse, and we'll do examples, and you're going to be like, wow, that's not only easy, it's kind of fun. Okay, so now I gave you a little handout there, and part of what we do this for is, well, a couple of reasons. One is that a Hamiltonian is going to be proportional to J squared, where J is the total angular momentum, because of course it is. I mean, and of course the way that's going to work is it's going to be L plus S, where this is going to be orbital, and that's going to be spin. Okay, so this is where we're going to be at the end. I just try to motivate it. So we need to have the total angular momentum. Okay. Now, one reason this is going to get complicated, if we have this situation, there's really not much to say. And S has an L of 0, so there's like nothing to worry about. It has a spin of 1/2, spin type angular momentum, so okay, that's fine, we're basically done. There's not much to talk about. There's even less to talk about because now the spin is 0. In fact, when you have like lower orbitals, when we're talking about electronic configuration of molecules or atoms, and we're going to stick with atoms, molecules are really the same, they're just more complicated, but the concepts are the same. When you have these lower orbitals filled, you don't need to worry about them at all because all the angular momenta are 0. So if you look at it, it's an S state, so there's no L's. And the up and down of the spins cancel each other out. So there's nothing to do here. There's nothing to really add. Everything's just 0. It gets more interesting when you go to higher, when you start doing P states. And worrying about how P states interact with P states is generally where a lot of chemistry comes from. The D states as well, but D's are the same as P's, just a little bit more complicated. So I'm just going to do P states. Okay, so anyway, so let's make this a little bit more complicated. Let me go from that state that's like nothing. Let's do this. So now I've got some complication because I don't need to worry about L's, but I do need to add S. I do need to add the S's. Now this is a half plus a half, so the total spin is 1. And I could also do that, so that's 1/2 plus 1/2 minus 1/2, so the total spin is 0. So notice, and again, I'm adding angular momentum. And so again, that sounds relatively easy. And we're going to talk a little bit more about this. I'm going to show you the formal quantum mechanical way to add these spins. This is what I'm going to do first. And as much as I just did it, right? I just, this is a singlet state technically because there's no spin. I just added the angular momentum, but I'm going to show you a formal quantum mechanical way to add angular momentum and give you the same thing. Now, why do that when it's so easy just to look at it? The answer is because when we complicate things like, a little disjointed, but when we complicate things by like when we're doing carbon, now this is getting complicated. All right, so again, I don't need to, if we're doing carbon, then technically, the shielding, right, does this. when we're doing carbon, again, these are filled, the total angular momentum, there's nothing to do here. So when we get here, it gets more complicated. Now the reason is because the electrons, I have to add angular momentum. But I've got 4 things to add. I got to add their S and I got to add their L's. So we're going to start out with a very simple thing that you don't even need to do this algorithm for. But we need it because we're going to apply it to this thing, which unfortunately is actually kind of shockingly complicated. It's just carbon, but it's shockingly complicated because we have to follow these rules of addition of angular momentum, and we have 4 of them to add. The S's and the L's. So anyway, that's why we do this. And because that also has to do with the energy. Another reason is that we need ways of classifying electronic structure. So it turns out that we largely do it with angular momentum. Because angular momentum not only is related to energy, so that's good. It's like I like a classification for a molecule, for an atom or a molecule that's related to the energy. And then that would be related to my spectra. That's the best possible way to do this. And it turns out angular momentum is the way to do that. So not only is this going to allow me to get the energy, I'm also going to come up with labels, which is how I classify things. That's what a label is. And you're going to do that. And again, I'm hoping you've seen this before. 2s plus 1, a term symbol, right? L and J, which is L plus S. Okay, so we're going to look at this and figure this out, and of course it's related to the energy, but that's actually kind of a separate issue. Okay, so anyway, I'm just trying to motivate why we're doing this, by the way. Let me review a little bit of what we did. So total, and I'm just going to stick with spin. So I'm just gonna, let's forget all this complication again, just foreshadowing. Let's just do a helium atom like that. So we're going to formally add these angular momenta. Again, I can do it in my head, 1, 0, right? So there's no L's, right? So this is easy, but I'm still going to add the angular momentum in a formal way because again, it's going to get more complicated. Okay, so the problem comes about because to get the total angular momentum, I'm going to need to have a wave function, and I have hydrogen wave functions, and they may not quite be correct for helium, but they're close enough. And to get the total angular momentum, I've got to do this. And unfortunately, those are unknown, so I'm screwed. And by the way, I'm just talking about 1 electron at this point. I haven't even added the second one in yet. So what the hell am I going to do? Now, what we did was we introduced S plus and S minus, raising and lowering operators, and again, through some, a bit of algebra, which wasn't hopefully too bad. What we found was that you can do this. Again, it was just some algebra. That we can now get the total spin using just SZ, which is great. Plus and minus in SC, where our X and Y's are hidden in here. The good news is that plus and minus are Eigenstates. Now remember here, again, you've got a giant problem. You can't apply plus and minus. You can't apply our SC basis to X and Y because they're not eigenstates. So that's why you're so screwed with this representation. You're stuck here. If you don't get the eigenvalue equation to work, you're mathematical junk. You've integrated incorrectly, basically. But this is a resolution. Now here's another thing that's important to realize is that I understand plus and minus. See, I'm able, based on my high school level knowledge, I can draw this. I can start here. That is this, and now I have a way of getting the total angular momentum, which gives me a method of classification, because that's here. and can be related to the energy. It turns out the triplet's lower in energy due to spin-orbit coupling. I didn't mention spin-orbit coupling, but that was actually kind of bad. I should save that for Friday. So anyway, yeah, so what have we got with this? We've got, so we can apply the total angular momentum. And again, just because vectors always add as the square, r squared is x squared plus y squared plus z squared. Well, I'm not really worried about spin. We always just do this with s squared. Take the square root to know just spin.
The sz squared is supposed to be positive, right?
What's that?
The sz squared.
Yeah, where's my... Yeah, I messed that up before, right? I did it again. This one?
Yes.
Yeah, I messed that up last time, didn't I? How did I?
Yeah.
I didn't. Yeah. Thanks. I transcribed my notes and I didn't fix them. God, it's such a simple, obvious algebra error. Sorry about that. Did it twice. Good going, huh? Okay, so again, these are obviously eigenstates, and notice how, and you'd actually seen this a long time ago, I don't know if you remember, and I pointed out then, as I'm pointing out now, that spin is just like angular momentum. Because it looks just like, you don't have to write this down, it looks just like h bar squared L times L plus 1, which is what you get when you apply L squared to a spherical harmonic. Gotta think about it. Right, when you have this spherical harmonic, which we tend to use the letter Y, and SPD, PX, PY, PZ, right? This is what you get. So this weird Stern-Gerlach spin up, spin down is behaving exactly like angular momentum. That's why it's going to add like angular momentum. Okay, so again, I'm gonna try to describe a singlet. That's a triplet and a singlet. So I want to formally add these together. And as I'm mentioning, this guy, these raising and lowering operators is essential to get the total angular momentum because I need the total angular momentum. The total angular momentum is going to be S1 plus S2. Let me, I'm kind of painting myself to a corner. I want to leave this up. I want to leave this up here. So let me, I think I've just screwed it up, but let's see how far I can get. Okay. So when I look at this, and I need to have just one wave function, even if it's that's just a bunch of wave functions multiplied. I have S1, which is 1/2, and then I have M sub S1, and that's 1/2. Then I have S2, which is 1/2. The S's, of course, will be the spin of electrons is always 1/2. And then the M sub S2, of course, could be plus or minus 1/2. Now this could be plus or minus 1/2 too, just the way I'm presenting this problem. This is definitely either configuration plus 1/2 H bar. And then I'm just the problem I'm giving you to understand this is that this one can be plus or minus. These are still half, that's 1/2, that's the way I did it, and that's plus or minus 1/2. So that's the nature of the problem, is to differentiate these two. And again, this is how I have represented this based on my high school knowledge. I can always generate, I'm perfectly capable of generating, electron levels from my high school knowledge. I'm perfectly capable of always writing in electrons as up and down. So I'm always perfectly capable of generating these states. This is, if you can't do this, then you didn't graduate high school chemistry. Okay, but now what we have to do is you're going to have to turn this into a state of total spin. So note that that's total spin. In the process, you're going to need the total spin z component, and so that's what we're going to actually have to get to. Is we're going to have to re-represent this as this, and so the question is how to do that. Now, why do I need to do this? Well, for one, I need to know the total spin. Okay, now let me just remind you. Let me do S1. Let me do the so these aren't operators, right? This is just the description of the wave function. So let's do the operation of S1 on. These are traditionally abbreviated in the following way. And these are traditionally abbreviated in this way. So be careful of that. Be careful of that. But they actually contain overlapping information. I kind of have to use this because it's going to drive me nuts otherwise. Okay, so S1 squared is going to be, again, we've already talked about this. So, of course, that's 3/4 h bar squared. Okay, likewise, S2 on the state is still also 3/4. And again, this abbreviation is unfortunate because, what the hell? Oh, no, that was right. Sorry, I'm using this one. You see, I know S1 and S2, so of course I know what the effect of the operators are. Okay, now I hinted at this last time. Is it S2 squared? Oh, S2 squared, right, yeah, thank you. Okay. Yeah, I get kind of flummoxy. This is really a tough one. So total spin squared, which again, I can't emphasize enough, is of paramount importance to know, because these, again, is while I know these, it's like, well, if you know these, then why aren't you done? Then just add these two numbers together. Well, okay, so let's take spin and say it's S1 plus S2. And, for the operators, the problem is that, again, the way vectors add, you're doing that. And vector calc is such that this is S1 squared plus S2 squared, which again, it's like, oh yeah, well, I'm done now, right? Well, here's the problem. It's that cross term. It's that cross term that's going to create a hideous nightmare. And what's really happening here is the uncertainty principle. The uncertainty principle is going to result in a giant problem. Okay, so now let me explain why, and that's because S1 dot S2 is going to be so again, as I mentioned last time, when I look at that kind of stuff, I dot product from calc, vector calc. Okay, I had that freshman year of college, but I forget it. So I need a reminder. So here's your reminder. So it starts out looking not too bad. Okay, just operator after operator. Now again, as I mentioned, here's your x and y. You see, you're screwed. You're screwed. You can't get the total spin based on this wave function because you don't know what the x and y components are for one or the other. So what the heck are you going to do, right? Now again, it turns out the raising and lowering operators going to solve this, and I'm not going to do all the algebra, but what it comes down to equals, I don't know what to do. Okay, so it turns out that you can recast this in this way, and again, I hope you don't mind if I don't do all the algebra. So it's going to be S1, S2, Z component. The only thing I do know, and then guess what? Then it's going to be in these raising and lowering operators. And guess what? You're actually cool with those. So, are you? Wait a minute. Sorry. I may have spoke there. Well, all right, hold on. With this information, so you combine these two, and now S squared. Sorry, I may have just misspoke. Okay, so S squared is S1 squared. Again, I know what that is. It's 2 squared plus 2. Okay, so up until now, I'm kind of okay. I know based on, I draw this based on high school knowledge, but that basically means I know this. That means I know what S1 is, 3/4 h bar squared. That's 3/4 h bar squared. That one is plus 1/2 h bar. That one here is plus 1/2 h bar. Here is minus 1/2 h bar. You see how I know these. I know these, right? Now, hold on, I'm not done yet. Okay, then I've got these raising and lowering operators. And again, remember what these are hiding the x and y components in ways that are tractable. Okay. And so I misspoke earlier. And now that I have this, what you find is that if you know S1, the S1 operator and the S squared operator commute. The total spin on the second deal and the S squared operator commute. However, sorry, I misspoke a little while ago. The S1Z and the total operator does not commute, as well as the S2Z and the total operator do not commute. Okay. Now, let's see here. Okay. So now, what's the big picture here? What's the big picture here is that what you've learned is that this doesn't work. All right, so like I say, we were cool with this information from our high school knowledge. We were cool, all right, couldn't. Now we don't know the total spin for this 2-electron system. Now we're screwed. Even though I actually do. I mean, I look at it and I know it, but quantum mechanically I don't. So this is kind of Donko nutso. Again, I cannot use my known wave functions and solve this. This is not the eigenfunction for this operator, and so I don't know anything. Okay, now it turns out this is. So where this is S1, where this is right here, and this will be this. Now, what's the z component of anything, right? So if I said So you actually know what this is, right? So now we know what this is. We know what this is. It's the total spin, 3/4 h bar squared, square root, 3/4 h bar squared, square root of it. Okay, now this one's the only one that maybe looks like we don't quite know yet. Okay, if I tell you you have a p orbital and L is 1, what are the m sub L values? What are they? I mean, how many p orbitals do you have? 3. And well, okay, now d orbital. How many d orbitals?
5.
How do you know? Oh, okay, now why are there 3 and why are there 5?
Negative L to L.
Ah, okay, so SC would be, now hold on. All right, so m sub L is what? You were saying it?
Negative L.
Minus L.
0 L.
0.
Positive L.
Right, so -1, 0, +1, that's for P. For D states, it's -2, -1. Okay, this is, just say the same thing using
So it's from negative S to positive S?
negative S plus 1 to 0 to positive S plus 1. So you see, you actually, so if you can convert this into this representation, again, you automatically know that and that. That is what we're working on, and then that you actually will figure that out at that point. And when you have this representation, clearly you know what the total spin is. And when you have the total spin, you can classify things and calculate their energy. So that's ultimately what we're doing here. Okay, now to go from here to here, what you want to do is work in this basis set, because this you know what this is. And the total basis set will be a matrix where we're going to consider every configuration. Now, this configuration, let's see how many are there. Up, up, down, down, up, down, and down, up. Okay, so we're going to have a 4x4 matrix. We're going to create the S squared matrix in this basis set, and I can tell that it's going to be 4x4. Right? You see what I just did? So what I'm going to do is create an operator for S squared. I'm using this basis set, and then I'm going to calculate its eigenstates and eigenvalues. And those will be the eigenstates and eigenvalues of S squared, and they're going to end up being linear combinations of these states. Well, that's it. They're just going to be linear combinations of those states. So again, so what we're going to do is calculate the S squared matrix. And we're going to be using the basis set of plus plus. And you know what I mean by this, right? Minus plus, plus minus, minus minus, right? That's up, up, down, down, up, down, down, up. Okay. Now, as I mentioned before, you need this SOB right here to determine this matrix. Because again, you can't use the X, Y, and Z form. You can't use the X, Y, you can't use any of these forms because they have X's and Y's in them. But this plus minus deal you can deal with. So the point of plus and minus, the raising and lowering operators, is now you can determine stuff like this. You couldn't do it otherwise. And so what that is now, as I mentioned last time, this is actually kind of freakishly difficult. I mean, you can see it right here, right? And I told you what S plus and S minus are. But I can tell you that this actually takes a long time. Okay, so there's one of our matrix elements. Okay, now let's do one other matrix element. Let's do plus minus. Oh, sorry, that was plus plus, my bad. Okay. Okay, so the thing here is, notice that you have raising and lowering operators. S squared has raising and lowering operators. This is where it's going to get complicated. So in this case, what you're going to have is, so we have S1 squared plus S2 squared. Again, those are easy. And because of the raising and lowering operators, you're going to have this happen. You just got yourself an off-diagonal element. Uh-oh. And this ends up being, let me just h bar squared. There we go. And on and on and on. Okay. All right. Now I'm just, what I'm just doing is I'm just walking you through making the matrix elements. But again, I hope I wouldn't have to do that, but just to make sure we're all on the same page. Okay, so now let me construct S squared. Let me show you what it is, and this is going to kind of suck. Let me make sure, now we need to make certain that we know how our basis functions are corresponding to our draws and tets and where on the row they are. Okay, so you see we've got a 4x4 matrix. It goes like this: 2, 0, 0, 0, 0, 0, 0, 1, 1, 1, 1, 2. Okay, so S squared, again, big picture, need to know what its eigenstates are because of vectors, because of the uncertainty principle. You got off diagonal elements in the basis set that you're most familiar with, which is your electron diagrams from high school. It's off diagonal because you don't know what x and y are. You can use these raising and lowering operators as a fix-it, but the fix-it has created off diagonal elements, and that means that it's complicated. It's as complicated as this. You set this up in MATLAB, and what are the eigenvalues? Eigenvalues, it is 2 and 0. Do that with MATLAB. Of course, that means S squared is 2 or let's see, does that make sense? Okay. Now we know that S squared on a wave function is going to return. Sorry, you know this is h bar squared, right? I'm gonna forget the h bar or h bar squared all the time, but we know that the spin squared is h bar squared s times s plus 1 wave function. Okay, so let's see here. If 0, then s would be what? S times s plus 1. How do you make that 0? Right, that's easy. That's easy. Okay, now it gets a little bit more fun. If s squared is 2, s is what? Not 2, it's 1. 1 times 2. 1 times 2. Okay, now I'm bringing this up because remember we're doing 1s2. We're doing a helium atom, an excited helium atom. All right. Now, how do I generate a total spin of 0? Yeah. Down up as well. So it's actually looks like there's more than one of these. And then how do I do a total spin of 1? Yeah, up, or down, down. And there's actually another way, but anyway, I'm getting ahead of myself. Okay, so remember I was saying I can draw these high school electron energy diagrams, and I can see singlet and triplet. I mean, look at the crazy expense I just went to. It's cool that it's working. I like that. It's cool that it works. But it seems like I went through a way complicated thing to, that's, again, I already know that's triplet. I know that's an S of 1, and therefore an S squared of 2. So all of this is, making sense. But why the hell did I do this? For one, I already mentioned that we're going to do way more complicated things than this. And you go through this whole procedure again. And you absolutely will have to. I mean, yes, I can add half plus a half. I am capable of that since probably the first grade. But when we start to get into more complicated things, that magic is going to go away. It's going to be way more complicated. But now here's another thing. I get eigenvalues. What else do I get out of the matrix? There's two things in an eigenvalue equation matrix thing. What do you get? You get eigenvalues and eigenstates. Oh, now this is going to get way more interesting. So let's look at the S squared 0. Let's look at the eigenstates. There's only one. It is 1 over square root of 2. Again, MATLAB tells me this. And so now let's represent this in S sub z. Now remember that there's S1 and S2, but we're not going to represent, we tend not to represent those. Okay, so S is what? We just did it. Okay, what's S sub z? Yeah, it has to be 0. Remember we just talked about that. Okay, so MATLAB said there's only one S equals 0 state singlet, and that's it. So cool. Plus minus. There you go. Now, one of the things I want to mention to you is as you read papers on molecular orbitals, you see things like this done. You see this, like here's your high school electron levels, and I'm adding and subtracting them. Well, why are you adding and subtracting them? Because those are the states of the Hamiltonian, because the Hamiltonian cares about total spin squared, not your 12th grade high school understanding of where electrons go. Okay. Now guess what? Now this is where it gets way more cool. Guess how many triplet states it finds? Here's a big hint. I called it a triplet state. There's 3 of these bastards. So, oh, I shouldn't call it that. Anyway, there's 3 of these bastards. Okay. Okay, there it is. Plus, plus. I don't need a coefficient for that. And there's minus, minus. And then it gets a bit more interesting. By the way, that's why we call it a triplet. There's 3 of them. I have little commas. Okay. All right, now let's represent this in its new basis form. In this S, total S and SC. Okay, so what would this be? It's not S, not S squared. It really probably should be S squared, but that's just not how people do it. 1. Okay, now what do you think SZ is? Now hold on. What are the possibilities? If this was a P state, you have how many P states? 3, right? Now L of P is 1. What are the M's of L states?
Minus 1, 0,
Minus 1, 0, and plus 1. 0 is a PZ state, and PX and PY are linear combinations of plus and minus 1. Okay, now looking at this one and seeing that the angular momentum, by the way, is 1 just like a P state, what do you think the SZ is? Looking at that this is up and up, and these are P's, and these are SZs. Huh? 1. Yeah, 1. Half. Okay, now this one is going to be
minus 1.
right, and then of course this is. You see? Now remember, I was also telling you, you've got to be able to make these designations correctly. Because this is how we're going to label, this is how we label things in chemistry based on their total angular momentum, which is again, this is how this is done. And it's also related to the energy. It turns out now, as we get into spin orbit coupling next time, triplets are going to be lower than the singlets. And again, that's a spin orbit coupling thing. Actually, sorry, it's true for a couple of reasons, but spin orbit coupling form. So yeah, anyway, it's related to the total energy. I'm getting ahead of myself, so let me just back up. Okay, so now big picture here is again that our ability to draw electrons and orbitals based on our knowledge of high school is great, and will always start that way, but it ultimately is not useful because they're not going to give us eigenstates to Hamiltonian. Okay, so what you got to do is you got to get to total angular momentum. Well, sorry, that's not an operator. And so in the case that we were just doing, now I also want to emphasize that we were dealing with electrons and L equals 0. So I was just adding S's. I was just adding spin angular momentum. I gave you an easy problem because I didn't have an L. I didn't have P state. Now we're going to do a P state. We're still going to have our S. This complication still exists, but now I'm going to add one more layer because now I'm going to put it in the P state. Now I got to do this and add in an L. Add the L's in. So now remember I said I got 4 things. Realistically, for things that are remotely interesting, like carbon, it's got P states. So I ignored that up until this point. But anyway. Okay, so the way this is going to work. S1, and M1, S2. Hopefully I'm being consistent on my I hope I'm being consistent on my notation here. I may not be. So again, these things, which oh sorry, I didn't see. I told you. It's the abbreviation. I hate that abbreviation. Let's get rid of this. Okay. So again, remember that you never see these. You just don't see them written into the kets in paper. So, but I do want you to know that you didn't like lose information or something like that. You really can't do that. Okay. So what we've done is we've taken these things that we know from high school and made linear combinations into the things that are actually eigenstates of the Hamiltonian, because that's what you gotta have. Now that's here. That's here. That's our 1, minus 1, 0, plus 1. And it's a linear combination of the thing, of the, did I just screwed that up? God, sorry. Just screwed that. It's a linear combination of what we know, which is S1. Right, these are these. Okay. Now, these things are called Clebsch-Gordon coefficients. Now, you may have just noticed, because it happened about 10 minutes ago, the complication of creating a total angular momentum operator, and then creating a matrix for it, and then doing the eigenvalues. Okay, but at the same time, eigenvalue of a matrix, I think that you're okay with that. It just was fair to create it. Clebsch-Gordon have taken every possible combination of angular momentum you could ever run into, and they've done all the tables. They've done all the matrices. I told you, this is actually shockingly easy. What you're gonna do is you're gonna come up with any sort of electron configuration, which again, from your high school knowledge, look it up on a Clebsch-Gordon table and then be able to put it into a configuration that's an actual eigenstate of the Hamiltonian. When it's added correctly. So Clebsch-Gordon took all of your configurations you ever come up with and added them such that you don't actually have to do any of this. So this is actually shockingly easy. Okay, in the time I have left, again, I took an example, 2 electrons, one in an S, one in a 1s, one in a 2s, which are either singlet and triplet, and we've gone through all the quantum mechanics. We've seen that, yes, we have singlets and triplets, and you can see that you have 1 singlet state and 2 triplet states, which is kind of cool. We knew how to do it, now you see all the quantum mechanics of it. Now we're going to do a 2p1 state. Okay, so what does that look like? Okay, so I've got 1s. Okay, I don't care about that. This is a multi-electron atom, so the 2s is lower than the 2p. And I'm going to just have one spin up. Okay, so now I'm going to be adding s and l. Now, last time I added 2 s's because that's the problem I had. Here, I don't have to add 2 s's because all my lower states are filled and all these angular momentums are 0. And I don't need to even consider that when it comes to creating a designation for that, which again will be a term symbol. I need to create a term symbol for this. I need to actually think about every term symbol because I got 1, 2, 3, and then I've got them. Actually, I have 6 of these, right? Up, 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 down, down, down. I have 6. So I actually need to figure out 6 different term symbols. And depending on which one I have, then I can figure out its term symbol. If I know that this, notice that I've done something very specific here. I've created a very specific state. I need its term symbol, and then I can look up its energy. So that's our goal here. Now, let's see here. Okay, so in this case, we are going to go from a basis of, what do we know? We know L squared, let's call it L, LZ. Oh, not an operator. S, and SC. Okay, so we know this, and what we're going to want to get from there. So I know this. I know it's a p state. In this case, I drew it into the p plus 1 state. It's spin up 3/2 h squared or 3/2 h bar squared. And then it's plus h bar. So I know, see again, I can draw this and I can know this, but again, this is garbage. This is not going to tell me the energy. I have to convert this into to the L squared. Total, again, this, and then I'll have, again, why am I writing operators? Okay. Now again, remember, you know what, I really should be, no, what am I, sorry, I'm just all over the place sometimes. It's J, sorry. Got it, just painful from my perspective. Of course, J is L plus S. So that's the goal. Real quick, let me just show you. Let me show you how to do this for this state because this is easy. This one is actually stupid easy, but it gives you an idea of what we're trying to do. It doesn't help that I keep screwing it up. So again, L, LZ, S, S, Z, P, plus 1, 0, minus 1. That's always a half, plus or minus a half. You know that from this, but we have to convert it into this. Now, this is another case of one we don't actually need to do any Clebsch-Gordon this or that. We don't have to do anything too complicated. Let me just point out that I can, I'm gonna just do this +1, 0. What you need to do is consider all possibilities. This is why I gave you that. This is why I gave you that table, which we won't quite get to today. Let me just do spin up, because spin down is basically the same thing. Well, no, I'll do spin down. So you need to come up with every possible configuration when it comes to figuring out how to convert this to that, because you have to have this because that's related to your energy. Okay, so 1/2, 1/2, 1/2, minus 1/2, minus 1/2, minus 1/2, because look at it, right? Up, down. Interval 1, 0, minus 1, 1, 0, minus 1. Okay. All right. Now, real quickly, if I'm going to get to this, what's 2s plus 1? 2. So it's a doublet. 2, now I got to get to L. Okay, so this one is actually going to be quite easy. What do you think L is for each one of these states? It's just 1. Just P. Okay, last bit. J is going to be, you're going to calculate this, what's called a Russell-Saunders. You probably have seen this before. Under Saunders coupling. And I'll explain a little bit more about this in a minute, next time. The way this works is you do L plus S, down to L minus S. So what you have here, of course, is then 1 plus 1/2 to 1 minus 1/2. So you can either have P 3/2 or 2P 1/2. Okay. Now we need to account for 6 states. Does that happen? Now how many of these are there? Now remember that JZ is going to be dependent on this, right? So if J is 1/2, what are the possible JZ states? And now remember that spin, like an electron, single electron spin is 1/2. And how many states are there? Okay, so how many of these are there? Right. How many states are here? And that's a little bit more complicated because it's not an S or a P or a D. 4. 3/2, 1/2, minus 1/2, minus 3/2, right? Remember that? L, minus L plus 1, minus L plus 2, to plus, yeah, remember that? So it's 4. 4 and 6, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, there's 6 states. Okay, now that's all I got time for. What I'll do next time what we can do is look at the Clebsch-Gordon table and figure out what combinations of these states correspond to 2p-halves or 2p3-halves. And then we're going to do that handout, and I'm going to add an electron. We're going to do that one, and then we're done. Done for the class.